Okay, so what we're going to do today is we're going to take the same idea, but now we're going to apply it to a different type of function. These functions are called power functions, and a power function looks like this. It has a number times a variable being raised to a power. Okay? A, not surprisingly, hopefully, is called the power. K is the constant of variation. And that's all you need to know. Okay? So you have actually done a lot of these before in your lives. So you are familiar with these already?
Okay, I need to right now.
No, you gotta go faster.
Yeah, of course it didn't stop.
Okay, stop.
So if we look at the common, you look at the common formula, C equals 2 pi r, which is the formula for what? Circumference of a circle. What would be the power of that function? 1, because it's r to the first. And what is the constant of variation?
2.
Oh,
C.
2 pi, both of them. Okay? So r is the variable. It's being raised to the first power, so that means the power is 1. 2 pi is the constant of variation because it's everything that's not the variable. Okay?
Everything that's not the variable is
Everything that's not the variable is the constant.
So
Okay?
the power
How about a equals pi r squared, which is the formula for
No, it's going to be
area of a circle. The power is now
2 and the
2
constant is
pi.
5.
Good. And the constant is pi. Okay, this is one that you're probably not familiar with.
Wait, can you say anything that's not the variables?
Yep.
Friction.
That is a formula for the force of gravity.
I knew that one.
The force of gravity is called, it's an inverse square law. The farther away you get from the object, the weaker gravity is, and it's not direct variation, it's by the square. So if you get twice as far away from something, the gravity is actually a fourth as powerful, okay? And so what is the power in this case?
2.
Wrong,
Okay.
3,
wrong,
1.
wrong.
Did you solve it?
No.
Nope,
0.
nope.
D2. Negative.
Because it's on bottom.
-2 because it's on the bottom.
Oh, that's
Okay? Because another way that you could write this, since the variable is on the bottom, is k times d to the -2 power. Okay? And then the constant in this case is,
KD.
no, d is the variable.
K.
So it's just k. D is the variable. The variable is the distance that the two objects are away from each other.
Silly.
Okay, and then this is Boyle's law, which says that the volume of a gas varies inversely as the pressure it exerts on its container.
Power D.
Yeah, so the power is
Yeah.
-1, and the constant again is K. All right? So those are some simple examples of power functions. So let's take a look at some graphs of power functions. This graph on the screen right here is the graph of y equals x cubed. How would the graph change if I throw a number in front of there?
Well, it would.
There'll be a stretch. So if I go, for example, 4x cubed, this is all stuff that we've done before that you know already, then that would stretch it out to make it steeper. Okay? If I take that number and instead of making it a whole number, I make it a decimal, or a fraction in between 0 and 1, what will that do to the graph? It'll shrink it out. Or the other book calls it a compression, okay, because you're sort of squishing the graph. Either one is fine. What if I take that and make it negative? What will it do then? Flip it over the x-axis. And so there will be original one, and then this is the new one flipped over the x-axis, okay? And then please note that with power functions, I can't move it up or down, or to the left or to the right, because then it's no longer a power function, then it's a what?
Oh, that's
Polynomial, very good. Okay, so power functions is only a number times a variable being raised to a power. So as soon as you bring addition or subtraction in there, then things get revoked, okay? All right, so some things in life can be modeled with power functions. For example, the distance that planets are away from the sun. So I'm going to make a little scatter plot here of some values.
Should we play along or not?
No, you can just watch, listen, and learn. So these are the average distances of some different planets from the sun.
I think it's one big unit of measurement.
Yes, it is.
That's way too much.
It's almost not
Or like a pretty board. All the just love it.
Oh, man. I was thinking about that this morning. I can say this because Patricia's not here. To me, this is like living in California. I have to be outside a couple hours every day, and so usually I really have to track the weather, you know, to know what to wear and stuff. Just get up every day, throw a light jacket in the car, and we're good. It's been great. Yeah, it's been great.
Yeah, like look at that day, it's nice and clear. That would hurt. Actually, no, it wouldn't. Actually, my testing are good.
Yeah.
Hang on the back.
If you really must, if you could just hang on for a quick second, that would be awesome. Well, you use your, you gotta do what you gotta do. All right, can I get you guys back here? All right, so this, I guess this is a little bit hard to see because this last point way out here, but this is the relationship between the distances, what planets are from the sun, and the length of times of their orbits. And hopefully you can see that linear is not really a good way to go here. There's some points down here that you can't see, but it's going to make an upward curve like that, okay? And so this is a good one to do, to try to model with a, you could try a quadratic, but they would like us to model this with a power function. So we have the ability to do that. If you go stat, calc, and then you keep going down, there's one that says power, okay? So if I hit enter and then enter again, it gives us the formula that I put up on the board. It's changed the K to an A, but it's the same idea. So it tells us that A, or the constant of variation in this case, is about 0.2. So my equation would be y equals 0.2 times x, and then the power, since we're not restricted to whole numbers, is about 1.5. Okay, and that's pretty nifty because this is real world data. Look how close the correlation coefficient is to 1. So this is real world data that actually fits a very simple mathematical model very, very closely.
Yeah,
Okay?
isn't it
It is pretty interesting. What's that?
The closer to one, the better it is.
Closer to 1, the better it is. So then, if we wanted to figure this out for
Ow.
Neptune,
Question, so when these start to get off, that's when we're in trouble?
right?
Because like we're gonna get closer to the sun.
Oh, no, that's not going to ever happen.
Oh.
Okay, so if we wanted to figure out the orbit for Neptune, if we knew that its average distance from the sun was 4,497, where would you plug that number into the equation? in for the x, because the first column that we entered was the distances. So you plug that into the x, and then 4497. So if we go 0.2 times 4497, and then just use your little exponent button for the 1.5, and that gives you what you would predict the orbit of that planet. Okay? So, mostly the same stuff we did in the last section, just with a different type of function.
I like it.
Okay? Okay, you're off.
Wow.